flow rates of a hot and cold water streams running through a parallel flow heat exchanger are 0.2 and 0.5 kilograms. So we are having a heat exchanger, and this is the inner tube and there is an outer tube, and through the inner tube this hot water is moving, and that this is a parallel flow heat exchanger. So cold water, and this is the cold water, this is hot water. Through inner tube we have hot water, and they will be flowing in the parallel direction, and their mass flow rates are given. For hot water it is 0.2 and for cold water it is 0.5. So we will write that 0.2 and 0.5. Then inlet temperature of hot and cold sides are 75 degree and 20 degree. So inlet temperature of hot water is 75 degrees Celsius and inlet temperature of cold water is 20 degrees Celsius. Now also it is given in the question that the exit temperature of the hot water is 45. So hot water is going out with a temperature 45 degrees Celsius. Now remaining question, if the individual heat transfer coefficient on both sides are 650 degree, calculate the area of heat exchanger. That means here we are having a inlet hot tube. So inlet tube. For inlet tube there are two surfaces. One is inner surface and the other is outer surface. Usually in the question this inner radius and outer radius will be given. Here it is not given. So in the inner surface the heat transfer coefficient of H1 is equal to 650 degree, and in the outer surface too it is same, H2 is equal to 650 degree. That we will look. Calculate the area of heat exchanger. That is the question. So it is given that the hot water is entering with a mass flow rate 0.2 kilogram and entering temperature of 750 degree. When it is going out it is 45 degree. So that means it is liberating heat, and that heat will be is equal to mc delta T or mh means for hot mass flow rate of hot water, cph, that is c of hot water, th1 minus th2, change in temperature for hot water. So we will first calculate that. So that is mh is 0.2, cp for water it is 4187 into th1 minus th2, entering hot water temperature 75 minus outgoing hot water temperature 45. So we will get a Q. So this Q is the heat liberated because of this temperature change for hot water, and that heat liberated will be absorbed by the cold water. And for cold water actually the heat absorbed is equal to m into c into delta T. So m dot c it is represented so that it is for cold water. CPC. CP means this specific heat capacity, that is 4187, because in both cases it is water itself. So m we have 0.5, c we have 4187, Tc2 minus Tc1. Tc1 is the entering temperature for cold water, that is 20 degree we know, but we do not know Tc2. So we will be writing Tc2 as itself there, and Tc1 we have it is 20 degree. So on calculating it, we know the heat liberated by hot water, we know they can be equated to heat absorbed by the cold water, and at last we are able to find this Tc2. Now LMTD for parallel flow, for parallel or counter flow, this equation is same, theta 2 minus theta 1 by log theta 2 by theta 1. But here theta 2 is equal to th2 minus tc2 and theta 1 is equal to th minus tc1. So we have this th1, th2 and this1. These are given in question. Tc2 we have found. Then on substituting that we can find the theta 1 is equal to 55. 75 minus 20, 55. Theta 2 equal to th2 minus tc2, that is 45 minus 32, 13. So we have theta 2 and theta 1. Here substituting here we will get LMTD. So now we know Q is equal to UA theta m. This theta m is the LMTD temperature. Theta m. So we have theta m. We are asked to find the area of heat exchanger, that is this A. So we want U. So U is given. U can be found out either by using inner surface as the base or outer surface as the base. Here anyway, this inner surface and outer surface, the radius are not given distinctly. So we will take that this tube is very fine one, so that this R1, Ri, Ro or inner surface and outer surface radius, here R1 and R2 are same. So here usually U1 is equal to U1 by the formula 1 by R1 into 1 divided by 1 by H1 R1 plus 1 by K log R2 by R1 plus 1 by H2 R2. So this is for the composite cylinders. This equation is written for composite cylinders. But here, this conductivity, about the conductivity of the stove, is not mentioned in the question. So we will neglect this term. And we are also taking R1 is approximately equal to R2 because here it is not in the question. There are no lines is given to this R1 and R2. So we will take R1 is equal to R2. Then what happens is the equation will be shrinking to U1 is equal to 1 by H1 plus 1 by H2. And also it is given that this heat transfer coefficient on both sides of the tube is 650. So that means H1 and H2 are 650. So we will substitute that here and we will get U. So U is obtained, theta is obtained. Now Q. Q is the heat exchange that have taken place. That is the same heat that is liberated by hot water or the heat absorbed by the hot water. That is the heat that have exchanged. So Q we know 25122. So 25,122 is equal to UA theta M. So U is 325, A we do not know, theta M we know. From that we can find A, and that A is the area of the heat exchanger. That's why we do this problem. Thank you.